I always start by reading carefully. Okay. We have 500 feet of fence, and we want to enclose a field against the wall of the barn. The field is to have two parallel lengths, so two straight sides of fencing, perpendicular to the wall, joined by a semicircle opposite the wall. So it's going to look like a basketball key, if that helps you. How do we maximize the area of this field? All right. So step one, write in the two words. So it's very clear what we're trying to do. We want to maximize area. Step two, draw a picture. Okay. Got our barn. Let's model that with a straight side there. Two long sides, maybe long, joined by a semicircle. Okay. We need to label things, so let's call the straight side, let's say that it has length x. Right, so this parallel side will also have length x. And then we have a semicircle here, and what characterizes a semicircle would be the radius. So this would be r, and this would also be r. So our rectangle has dimensions x by 2r. Okay. Now we need to come up with a function, okay, or a relationship. We have to write down what we want to optimize in terms of the variables. So we're trying to optimize area. So the area is going to be the sum of two pieces, the rectangular bit, right, which is length times width, so x times 2r, plus half of a circle. Well, a circle has area pi r squared, and we need 1/2 of that. Now notice here we've got two variables, and we're going to have to, in step 4, reduce our quantity to be optimized to one variable. So we need to find another relationship, a relationship between x and r that we could use to change this all to either x's or change it all to r's. And the relationship, the thing we haven't used yet, is that we have 500 feet of fence. Right. The fence goes all around the three sides here that I'm going to mark in red. Here, here, and here. Okay, so that total length has to be 500. Right, so 500 better equal 2x plus this half circumference. The circumference of a circle is 2 pi r, and we need half of that, so 1/2 of 2 pi r. Right, so I can use this relationship now. It tells me x and r are connected. I can solve this for one of the variables and substitute into the other. I'm going to solve for x because I see up here in my equation for the area that I have only one x to substitute. If I solve for r and substitute, I'd have to substitute in a couple places and do some more math. So I have 500 equals 2x plus pi r, or 500 minus pi r equals 2x, so divide by 2 equals x. Now we've got to substitute into our area equation. So we get area equals x, 500 minus pi r over 2 times 2r plus 1/2 pi r squared. These two's cancel. And let's do some cleanup now to get a nice simple function before we go and do any calculus. The area is equal to 500 r, I have to distribute the r here onto both pieces, minus pi r squared plus 1/2 pi r squared. These two terms can be combined, so I get area equals 500r minus 1/2 pi r squared. So here's my area function in terms of the one variable, the radius. What are the limits on r? Well, right, the next step here, what I want to do is find out the domain of my function that I'm trying to optimize. So to do that, I need to figure out what are reasonable limits for r. Right. So r has to be greater than or equal to 0. Is there an upper bound for r? Well, sure. If you made x equal to 0, then you would have the semicircle being everything. Right. So we need x to be greater than or equal to 0. But from right here, I know that that tells me 500 minus pi r over 2 has to be greater than or equal to 0, which is the same thing as saying 500 over pi is greater than or equal to r. So r is in the closed interval from 0 to 500 over pi. Now I have a continuous function on a closed interval, and so I can use the closed interval method to find the absolute max and the absolute min. So step 6 is where the only calculus occurs. Set that equal to 0, and I get r equals 500 over pi, which corresponds to one of the endpoints of our interval. That's okay, because in the closed interval method, what we do is we list the endpoints and the critical points. In this case, the critical point and the endpoint coincide, and we check the area at each. If I make r equals 0, I have 0 area, and that makes sense here. If I make r equals 0, then I just have two long parallel sides right next to each other. Right, I was pointing at the picture which you couldn't see. If you make r equals 0, then that means you're using all the fence to have a straight side, turn right around, and come right back. So you get 0 area there because that is 0 width. Right. And if I put in 500 over pi into my equation, I get 500 times 500 over pi minus 1/2 pi times 500 squared. This is 250,000 over pi minus 125,000 over pi is equal to 125,000 divided by pi feet squared, or square feet. And that's the absolute maximum area. The question above actually asks, let's make sure we answer the question. It actually asks, how do we maximize the area? All right, so if I'm going to give instructions to the farmer, all right, we tell the farmer that you're going to make r equals 500 over pi. You're going to use all the fence to make the semicircle, right? And when you do that, you get, when you plug in r equals 500 over pi, we're at the end point here. That corresponds to x being 0. So you're not going to use any straight sides. So build a large semicircle against the barn with radius 500 over pi feet. So no straight sides.